Okay, good evening. Today's lecture is on sequential models. So this is a new topic where we are dealing with inputs that are not static with respect to time, but changing with respect to time. Examples of sequential models are speech, which is a flow of sound signals, or it is language where we have a sequence of characters or words or phrases of text. That is, again, a sequence with respect to time. It could be a sequence of data points, let's say amount of snowfall on different days. And so you have a sequence of data. So how do we process these, and what kind of deep learning methods are appropriate for them? So it's a pretty exciting topic. There's a lot to this topic compared to processing static data, like a static image. What about a video image, right? So it's a much more complex problem. So it's a big topic, and we're going to spend a couple of weeks on this. So we will, I'm assuming that you all have had an exposure to convolutional neural networks, CNNs. It's a topic covered in the Introduction to Machine Learning course as well. The normal flow of things, CNN would have been chapter 9, and we're skipping chapter 9 and moving on to chapter 10, which is sequential networks. So here we will look at some simple models called recurrent neural networks, which can be regarded as the standard neural network, a feed-forward network, except there is a unfolding with respect to time of this network. So at one instant of time, you have one network, and in the next instant of time, you have another network, and so on. It's called the unfolded sequence. We look at a recurrent neural network in that way. We'll also talk about why it's called recurrent. It's a sequential model. And then we will compare it to a few other models that are also dealing with sequential data. One of which is called as LSTM, or a long short-term memory model. We'll look at that and compare RNN with LSTM. And then I will also introduce today briefly in the overview an introduction to a model called the attention model, where contextual information of the past is preserved to perform whatever task is to be done at a given moment. It's a big topic, as I said. These are all different subtopics requiring a full lecture of their own. But today is an overview of sequential models. So I'll touch upon all of these rather than simply leave each of these topics for a later time. So each of these topics will be expanded out, and we'll be spending the next couple of weeks on sequential models. Okay, let me.
Professor, there is a question.
Yeah.
I think some students want to know, like, what is the meaning of the MS grade?
Oh, okay. Okay. All right, I took this up right in the beginning of the class. I mentioned MS and MU. MS stands for mid-semester satisfactory, and MU stands for mid-semester unsatisfactory. It's not a binding grade. Okay, so for those of you who joined late, I went over this in the early part of the class today. All right, so we began with the discussion of MS, MU, and what you need to do, and also about the Thursday morning meetings. Okay, so you can also send questions on chat if you want, and we'll address some of those issues. Okay, so let me, if you have questions on the technical matter, go ahead and ask. Okay, we try to take up the organizational questions in the beginning of the class exactly at 5:30. Okay, so my line of thought got interrupted. Okay, so we were, I was about to begin with the lecture on sequential models. Okay, so the chapter 10 of deep learning is titled Sequence Modeling, Recurrent and Recursive Nets. So there is a specialized terminology here. So let us take a look at what these are. It's a huge topic. There are a dozen different topics listed here. Beyond that, there is a whole uh, chapter on natural language processing. So this is actually deserving of several lectures. So let us see how we can cover all of this material. Today, the introductory part is chapter number 0, sequential data and RNN overview. And this is an overview of recurrent neural networks. It'll cover a number of these topics. I'll mention along the way bidirectional RNNs, recurrent RNNs, and these kinds of things, LSTMs. I'll mention all of these things here, but these are all different subsections. We'll try and cover as much as possible. And after we finish all of this, we'll get into specifically natural language processing. So we will be touching upon natural language processing all along the way, but this is a more general talk about sequential data and not very specific to natural language. That will be the subsequent application. So examples of sequential data are manifold. I think you would have heard of this, maybe even in the introduction to machine learning course. And they often arise through measurement of time series. So we have acoustic features at successive time frames in speech recognition. So if you want the computer system to recognize what we are saying into a microphone, it would be using acoustic feature, successive time frame, time interval, sequence of characters in an English sentence, parts of speech of successive words. When you have successive words typed in, what parts of speech is it a noun or a verb or an adjective, an adverb, and etc. Snowfall measurement on successive days, rainfall measurement on successive days, daily values of currency exchange rate. All right, so one could have a process of what is happening to the dollar versus the euro rate or something like that. And nucleotide base pairs in a strand of DNA. So that's another sequential data. Here is a more specific examples of sequential data, and these kinds of models are to process such data. Speech recognition using a sound spectrogram. So there is a device called a sound spectrogram. If you speak into it, it produces a spectrogram like this. The x-axis is time and the y-axis is frequency. And at any given moment of time, there are many frequencies in what is being spoken. And this chart here, it's brighter if there is a higher density of lower frequencies, and so on. So this is higher frequencies, lesser density, and higher frequency, and then lower frequency. This is a male voice speaking the word 19th century. Okay, 19th century, and this is a sound spectrogram of that. So so how, this is sequential data coming in, and this is not only with respect to time one value, but we have multiple values and processing all of these simultaneously to recognize what is being said. That's an example of speech recognition using a sound spectrogram. Natural language processing is, I suppose, compared to that task, it's somewhat simpler. One example is named entity recognition. If I give you an input sentence, Jim bought 300 shares of Acme Corp in 2006. Named entity recognition is to label these words as to what type of a entity it is. You would recognize that Jim is the name of a person, and then Acme Corp is the name of an organization, I guess a company. And then 2006 is some point of time. So named entity recognition is to be able to name what kind of an entity some of these items are. May not be all, but these are like all proper nouns, right? Jim and Acme Corp, so on. Another example of speech NLP task with sequential data is machine translation with a sentence "Acte dicke Christe" mean German is translated into English as awesome sauce. Okay, that is sequence to sequence task. These are all sequential models that are used for them. Sequence to symbol, examples of sequence to symbol are we go from a sequence as input and we're just getting one value as output. Like if there is a sequence that says best movie ever as a movie review, we would say, well, that must be a positive sentiment about that review. Another example of sequence to symbol is speaker recognition, where you take a sound spectrogram like we just saw here, and you would not be interested in saying what is being said. Like this said 19th century. Instead, you're recognizing who's the speaker, right? Can you recognize the voice of the person? That is again is sequence to symbol. And there could be, more complex sequence to symbol problem like textual entailment. Uh, Positive textual entailment means text entails hypothesis, and negative entailment means text contradicts hypothesis. And the text could be like Peter buys the car is the text, and the hypothesis is that Peter owns the car. And so if the text that you have entails the hypothesis, then we say it's a positive and negative. So in a sense, the relationship between a couple of sentences is a textual entailment with yes or no, a positive or negative type of thing. Anyway, these are all examples of sequential data to be processed, and deep learning is now being very widely used for these types of tasks. This is just another example of sound spectrogram to word sequence. This is someone is speaking Bayes' theorem. So this is a sound spectrogram. This is with respect to time, and we have a plot with respect to frequency. We're going from 2000 to 10,000 hertz. And there is a predominance perhaps here of the lower, probably male voice again. The colors here indicate the density of that particular frequency here. So so there are lower frequencies here, and then higher frequencies over here, and so on. And amplitude is also the sound amplitude that is also being plotted here. I suppose that can be obtained from the sound spectrogram. This is again Bayes' theorem. And the objective of the recognition would be to take this as input and says that's the sound of B and EY and sound of Z and then sound of TH, IH, Bayes, the whole thing is Bayes' theorem, right? Recognition of that from going from this image, from the spectrogram to the text. All right, here is, now let's get into a little bit of how deep learning is used in a very simple way to begin with, and then we'll look at these architectures more carefully. So this one was about speaker recognition with a convolutional neural network. So we have here a sequence sound spectrogram of somebody speaking. So it's being processed by a convolutional neural network to obtain a set of features here. And these features are being used by a support vector machine, a classic non-neural network type of method, to recognize who the speaker is, right? There are three possible outputs here. Now, again, this is just an expansion of the diagram for the convolutional neural network, where we take the sound spectrogram and obtain several parallel values here corresponding to different values for a kernel. If you recall, what a convolutional neural network does is you're passing a kernel over it of a certain set of values, and so each kernel gives rise to another output. So there are like 5 kernels being used here, 1, 2, 3, 4, I guess 4 kernels being used. It's a 3 by 3 kernel is being used for the convolutional layer. And that creates from this input, 4 sets of values here. And there's one more convolutional layer being used for the particular architecture that was used. And then there is what is called as a max pooling layer, which reduces the amount of information in all of these to obtain a max pooling layer. And then again, we have convolutional layer. I guess it's doing that with all of these 4, applying max pooling to create, I suppose, looks like it is 8 of these here, and again, 8 of them here, max pooling, anyway, generating finally. So anyway, this is the architecture that they particularly experimented, must have tried it out, saying these provide a good set of features to do the final task. So we go from this input to a set of features to do the task. So there's speaker recognition with the CNN. And well, what is going on here is this whole thing is being regarded as a static image, it looks like, right? It's not essentially dealing with the time series. Here is another elementary example of a time series being processed with a convolutional neural network type of architecture. The time series is an input sequence x0, x1, x2, x3, x4, x5, x6, x7, x8. And this is being processed to an output sequence y0, y1, y2, y3, y4, y5, y6, y7, where some dependencies are being used. This could be, an idea. We're going from sequence to sequence. We saw some examples of sequence to sequence, machine translation being one of them, or speech recognition being another. And so what's happening here is this is a particular network here that takes as input the x0 and x1 and providing weights W0 and W1. I guess we could think of this as a W transpose X, where W is of size 2 and X is of size 2. Take the product, do a sigmoid, and you get a Y0 out of it, right? And yeah, similarly, the next two. What is essentially happening is if you have this kind of an architecture, where only you're remembering the previous value, using it, remember the previous value, using it, and so on. Essentially, this is equivalent to a convolutional neural network with a kernel which is of the form zeros W1, W0. So the Y0 is sigmoid of W0 X0 plus W1 X1, right? We can also write the equations as Y0, Y1 as sigmoid of a matrix W whose elements are these. W0 is the diagonal elements and W1 are this next diagonal here. And so W0, W01 are the elements of this matrix. So we are performing this operation. So this shows an elementary example of processing a sequence where the only context we are using is an adjacent element that is used in the time sequence. And that can actually be done, not in a sequential way, but in the traditional way of a convolutional neural network, where we are simply processing this input by a matrix. And it's no different from a standard neural network. And so that's just an elementary example. We're going to go to more complex models. Another historically useful architecture that has been used for processing sequential data is something called a time delay neural network, or a TDNN, or for a temporal sequence. So the whole issue here becomes, when you process an element, you got to have some context of the past behind it. And how do we do that rather than simply think of one at a time? So here is an architecture people thought of early on, where we have the value 1 at time t, value 1 again at time t minus 1, and value 1 at time. So can't we use the value at time t minus 1, t minus 2, and t, all three of them together, to form an input at the next layer? This is value 2. what happens to that as time changes. Perhaps each of the value one could be, a pixel or a element in the data. And we are remembering what was there at the previous time and the previous time to that. And we are processing that value, how it has been changing, and then feeding all of them together to a hidden node, and so on, providing an output. That's a way of handling time sequence, except how much of a look back you need. So a TDNN, or a time delay neural network, remembers the previous few training examples and uses them as input into the network. Right? So you can think of them in a previous example, or if it's a time sequence, I suppose each of them would be a time frame. And so we are presenting the time frame now. The network then works like a feed forward back propagation. So this would be no different from a feed forward type of network, and we are processing these data in the same way. The recurrent neural network, which forms the basis for the most important model in this method, in this series of methods, or the earliest one, I should say, they share parameters in a different way than time delay neural networks. So each member of an output is a function of previous members of output. All right. So it says we can think of a network that is dependent on time like this. We have an input xt, output ht. We denoted h as hidden. It could be input to another layer. So an input x gets processed into an output h. And we're going through a node here which has got a feedback path. So this says we are taking this element input here, processing by what was produced the previous time around, and then that produces the output ht. All right. So each member of output is a function of previous members of output. And each output produces is produced using same update rule applied to previous. That's an important point, that whatever were the set of weights that were used here for x and the previous value, that is again being used eventually in the feed forward network. This is the formulation. And the recurrent formulation results in sharing of parameters through a deep computational graph. We can think of this network with a feedback path as being unrolled. This is called an unrolling. At x naught goes to a, we get an h naught, and we feed whatever a was computing to the next stage. So that value that we had, the feedback path, is going on to another point of time where x1 is being processed into h1 by not only using x1, but also the previous value of a, previous value that was provided, right? Previous output, that's h naught. But this, so we are using h naught in computing h1 with a given set of weights. And then again repeating h1 at the next stage, given set of weights. And h1 is, so in a sense, we are using this it's a recurrent formulation. The same computation is used again and again. This computation is a recurrent. We say that what was computed at the previous step is the same computation, except the value generated by the previous step is being used. So that's why it's called a recurrent network. And so the parameters are being used here in this way, as opposed to the TDNN, which was kind of accumulating all of them together with the inputs and then processing it once. Here we are completely processing it to the output. So the use of the parameters here are different, we say. RNNs share parameters in a different way than TDNN. Anyway, RNN is more important than TDNN. So recurrent neural networks process, so each of them is, you can think of a neural network, each time instant, we have a process that's going from the input to the output. So it is also a neural network, but it's recurrent. So recurrent networks are a family of neural networks of sequential data. And we can also think of an analogy with convolutional neural networks. So so they are also specialized architectures. CNN is a specialized architecture for a grid of values, an image, right? We present an image and we process it, we multiply it by a matrix to get the next layer, and then we multiply it by another matrix to get the next layer. That's what a convolutional network does. Except the kind of matrix we are multiplying it in CNN is passing along a kernel, which multiplies regions with the same set of values. So it assumes that there's some kind of a grid of values is available when we are passing along the kernel, left to right, top to bottom. RNN is specialized for a sequence of values, x1 through xt. So in a way, you can think of CNN as structured data, looking at, let's say, a two-dimensional object. A recurrent neural network, similarly, structured data, except we have structure with respect to time. And also there is scaling and variable length with RNNs, just like in CNNs, we can have images that are scaled. CNNs readily scale to images with large width, height, by appropriately changing the kernel, and the padding and things like that. Those come into play with convolutional neural networks. RNN scale to longer sequences than would be practical for networks without sequence-based specialization. Here again, the input may be a variable length, and RNNs can also be scaled. What you learn from a given set of training data can be used for variable length sequences that are input. And so that is not an issue. So RNNs can also process variable length sequences. So the important step with RNN is that they share the same weights across time steps. I already mentioned that when we compared it with time delay neural networks, that when we go from one time step to the next time step, the weights or the parameters are what was used at the previous step. So to go from multi-layer networks to RNNs, multi-layer, the standard CNNs we've seen, or deep networks, need to share parameters across different parts of a model. So we're sharing parameters here. One of the merits of convolutional neural networks is that they share parameters in terms of across the entire input. And that is considered an important tool to keep track, to lower the computational complexity, but also to relate different parts of the image in a similar way. So here again, separate parameters for each value cannot generalize to sequential lengths not seen during training. So we are using the same set of parameters. Share statistical strength across different sequence lengths and across different positions in time. So there is an interesting analogy. While a CNN shares the weights across the whole image from different points spatially, here we're using weights across different points temporally or in different positions in time. And this sharing is important when information can occur at multiple positions in the given sequence. So given I went to Nepal in 1999, and in 1999 I went to Nepal, machine learning method to extract year should not extract 1999, whether in position 6 or position 2, right? So in the sense, the network which is being processed one word at a time going through the network has to be able to keep track of words irrespective of whether it's the first word or second. So the parameters are not different for each time instance. So the same parameters are being extracted. So a feed-forward network that processes sequences of fixed length would have to learn all the rules of the language separately at each position. So yeah, this is not like processing 6 words only or 7 words only. So an RNN shares the same weights across several time steps. So again, that's being re-emphasized again and again, that the same set of weights are being used across each time step. Okay, now unfolding computational graphs is going to be a topic which will come up after we finish the major part of today's introductory lecture. But here is a quick preview of unfolding a computational graph. We can think of a recurrent neural network in a standard way as the leftmost diagram here, where you have X as an input and Y as an output. That's very similar to all the deep networks computational graphs we have seen. X gets processed to H, some hidden values. U is a set of matrix multiplication values that takes X to H. And H is again multiplied by another set of values V to produce an O, which is the output. What is this stuff here is Y is the training input in a supervision signal here. And L would be the loss function here, which takes what is being output by the model and what it should be. It resolves the two. And that's for the purpose of backprop to train this network back to figure out what the values of the matrices V and U should be. The only thing here is there is a W going out here. That is a set, there's a W matrix here that's multiplying this H, and that's feeding back here. So we have this remembrance going on over here. And that is being unfolded in this computational graph, saying what is happening here is X at time t minus 1 is processed to get HT time t minus 1, and then OT time t minus 1, and LT time as t minus 1, and YT time t minus 1. And this H at time t minus 1 is being fed to the next step. This is H at time t. All right, so H at time t not only is using X at time t, but also the H at time t minus 1, and also a set of weights W. So we got not only the weights U and the weights V, but all the weights W. They've shown here as a phantom H t minus 2, which may or may not be there, which is probably all zero values at that point. And that's being used at time t minus 1, and so on. Again and again, we are using that. So in a way, this kind of gives you a sense for what is the computation involved in a time series. And it also gives you an idea of what might be involved in training such a network, which has a time dependency, which is saying there's a loss function here at time t minus 1, loss at time t minus t, loss at time t plus 1. And those would have to be fed back here to update all the parameters involved. Okay. So we extend computational graphs to include cycles. Cycles represent the influence of the present value of a variable on its own value at a future step. Again, in a computational graph, which we've seen before, nodes are variables and operations. And here is an RNN to map input sequence X values to output sequence O values. Loss L measures how far each output O is from the training target Y. That's what this is doing. And forward propagation is given as follows. So what is forward prop? Is for each time step t equal to 1 to t equal to t, for each time step, let's say is the first one here, apply the following equations. O of t is equal to C plus VH. So this is saying it is a context C plus some weights V times H, what's coming in as H. So it is also using a context over here that is being used, which is the previous information here, the context plus VH. And H is itself obtained as tan H of AT. Tan H is, remember, it's one of those activation functions which produces a value between +1 and -1. And A is the augment to this tan H. And what is this A? Is a bias B plus WHT minus 1. Okay, that is this quantity. This we are talking about a time t here. So it's a W times HT minus 1 plus U times X, right? So that is what is being given as input to H. And H is a tan H. That's after the activation, the output is produced by taking the H value, multiplying it by V, and also taking into account a context C as in account, which is, I suppose, not shown here because H has already been taken into account. So C is being taken into account in producing this oh, what was the context in the past? That's a very useful quantity for us, because when we talk about more sophisticated models, such as LSTMs and attention models, this idea is going to play a role. But this is the essential computational graph for a recurrent neural network. That's the foundation for this whole area. So RNN operating on a sequence. RNNs operate on a sequence that contain a vector xt with time step. So we no longer have simple x as input. We previously had x as input. We have x super t, that we have superscript t indicating that is x at time t. And with time step t ranging from 1 to tau, some set of values. Tau is the length of the time sequence. And RNNs operate on mini batches of sequences of length tau. So this is saying we can think of it as a mini batch. Maybe some padding is needed to input it to one at a time or two at a time or a group at a time. It becomes a mini batch now. And that is when we adjust the loss function. So we take all the outputs into account for each sequence, and we would have to group them together, compute the loss function, feed them back. So some remarks about sequences is that the steps need not refer to passage of time in the real world. As although we indicated it's all about sequence with respect to time, RNNs can also be applied in 2 dimensions across spatial data sets, such as an image. You can think of an image also as a single image, as a time sequence by doing a raster scan from left to right, top to bottom, so on. So that would be a kind of simulating a time sequence. Even when applied to time sequences, network may have connections going backward in time. So we may have, it's not like we're just processing at time t and we don't have a look at the previous data. So we can have, it could be that we provide the entire sequence is observed before it is provided to the network. So the whole thing is available. So one could think of processing it from left to right, or we can also think of processing it from right to left. So if you have a network that does both, you see what is the dependence of the previous to this one. So how is the past context influencing this? Let's say we're doing machine translation. We're translating from German to English. When we're translating a word, we don't want to translate the word on its own. So what is the context in which it is occurring? And that gives some indication of the meaning to get the right word as output. Similarly, in speech also, we want to look at the context in which it is being spoken. And what about the context of at a future point of time? We might be saying, okay, now I can recognize it based on the past. So we can have context, or we can look forward or look backward and so on. So that's why some of the networks are called bidirectional, looking left to right or looking right to left. And today, some of the popular architectures involve that context vector C and the bidirectionality. And this leads to some of the most sophisticated methods of today for processing sequences. Okay, anyway, we'll look at some of the more fundamentals here. RNN as a network with cycles. So we can think of a simplistic diagram, x naught through some x4 here, input layer, and x4 and x something, xn, I suppose, yeah, xn here. And we are taking them as input, z naught, a simple recurrent neural network where we have a hidden layer producing the z's here. And then we have an output layer y. And we're saying the z's in turn go and allow us to compute these context values. And those context values are going back to the z's. So the z's now become a function of the x's and the context. This is more like the hidden values being used again, all right? So, so we can think of the context as just the previous values here, or we can also think of a separate context vector as well. So an RNN is a class of neural networks where connections between units form a directed cycle. We call this as a cycle in the sense it's going here and going backwards and forms a cycle. This creates an internal state of the network which allows it to exhibit dynamic temporal behavior. When we say temporal, it means it is a time sequence type of behavior, in the sense we are going, this is a time sequence, and each of them is remembering what was in the previous time step. The C naught coming back here, so on. And we can think of a network like this. An internal memory can be used to process arbitrary sequences of inputs. So these diagrams are all, from different sources, but they tell a continuing story. Here's another example that I found, RNN parameters. So here is an example of a folded network with cycles and an unfolded networks with 3 time steps. So let's take another look at this. So we have X is a vector input, and that vector input goes to a hidden layer set of values, and the hidden layer set of values goes to an output Y. So this is a standard feed-forward network with one hidden layer. So we take X and we multiply it by WHX values, which convert the values to H values. And the H values in turn are being processed here with WHH values as updates here to these from the previous step, from the previous time step. So this becomes, H becomes a function of the previous set of values as well as the set of inputs. And that in turn is processed by the W's to get Y, and that's being expanded out here. So we now have XT, XT minus 1, XT plus 1. At XT, we have WHX going in here, and then we have WHH is the way it's processing the previous time steps values here coming in. And then this HT is a function of WHH and WHX too. And then those values are processed with WYH to given this. And the equations are given here. HT, what is this HT? At time T is a function of WHH T minus 1, WHH HT minus 1. So this is HT minus 1, this set of values multiplied by WHH. And then we have WHX is these weights multiplying the XT. And what are these HT values? It's some activation function F of these two sets of values together. So this is how we are merging the two values, adding them together, computing. And what is this YT? Is we take as its argument WYH times HT. So whatever this HT is, multiply it by WH, and we are applying softmax to get that. What softmax again would be doing is taking the values here. So softmax is defined as EZI, the standard softmax definition. That is, this output has value, if the vector output, those vector values would add up to 1. And that's this normalization that goes on. So it's a vector output here, actually. So this is not softmax over all of these, it's softmax over just this vector involved in the outputs here, the product of these. So this is the nature of, so what are the parameters involved? We would have not only the W's with respect to the inputs, but we also have W's with respect to the hidden states and so on. That's a very basic sequential network. So unlike a feed-forward neural network, which uses different parameters at each layer, RNNs shares the same parameters WHX, WHH, WYH across all time steps. Notice that, that's what it's saying. WHH here, WHH here, WHH here, and this remaining WHX here. So it is using these same parameters across all time steps. So there is a sharing of parameters going on. It is not like different things are being computed at different time steps. So there is and then in that sense, they are capturing the past information in these matrices here, right? So it is not very specific to a particular length of sequence, which was a point that was being made earlier. Again, an interesting diagram, a very simplistic diagram about machine translation using that same idea. We have we have the word act being represented by this vector. We will talk about this when we do a little bit more on language processing, that every word gets mapped into a vector. We call it as word to vec. So the word here is mapped here, let's say into a vector of length 4, some reasonable size length vector. How it is done is, how do you convert a word into a vector? The word to vec algorithm would do that, which starts out by representing words in a vector called as a one hot vector, where you would have a vocabulary of 10,000 words, means there is a vector of 10,000 possibilities. One hot in the sense each word has a certain position. And so you would have a very sparse vector where only one of them is one and the rest are zeros. So that's a one hot vector. We start with that representation, and then we use some training data using context of these words, and that can be cleverly mapped into a small vector of any given length. In this case, it's shown as 4. It could be like typically maybe 300 is the length of a vector. So every word gets a unique vector that says what word of the language is that. And the amazing things about these, it's called an embedding then. And these embeddings are very interesting things, that meaningful things have similar vector representation because they have occurred together or something like that. Anyway, so words like Echt, Dicke, Kiste in German would be vectors that are being processed into, I mean, that's being called here as X1 vector. And it's we're also getting some H1 values from the previous time step, right? So I guess it's blank here. And the next one, Dicke, would have the context here coming in from the previous word being multiplied in, and then the previous word again. So this vector is capturing what was not the previous word, but also what was before that, because all that is influencing this. So this vector is influenced by not only the previous word, like this next one, for example, this Kiste is being influenced not only by Dick, but it's also being influenced by Echt. So it's being influenced, and it is producing, as we apply inputs to it, it is producing a sequential output here, that the words here are awesome sauce, that is Y1, Y2. So this is the input sequence, and that would be the output sequence. I guess the timing has to be done right here. X1, X2, X3 corresponds to Y1, Y2, and so all of that input is being processed. I suppose in the beginning we would have Ect going through, and then Dick going through, and then Kist going through, and all of that gets processed in the time sequence as awesome sauce. So it's an RNN for machine translation. So time sequences can be handled in this way by a whole set of numbers and vectors and so on. So length of time steps is determined by the length of the input. Example, if word sequence to be processed is a sentence of 6 words, RNN would be unfolded into a neural network with 6 time steps or layers. So if the word sequence is 6, one layer corresponds to a word, we can say. Theoretically, RNNs can make use of the information in arbitrarily long sequences. In practice, RNN is limited to looking back only a few time steps due to the vanishing gradient or exploding problem. Okay, so there is a practical issue comes into play, is how many words can you look back to process everything? And if you're going to be using back propagation, you would have to compute gradients. So we would have to say at every time step we are getting these outputs, we are comparing to what the output should be. If they're wrong, after a batch of inputs have come in, you have to go backwards, and you have to be computing gradients, and then gradients have to be passed. And we saw how gradients are computed, where we are multiplying the gradient for each connection with the next one, next one, next one. These are all small values, so they become vanishingly small, or they can become very large as well. And so these are all practical issues. So with an RNN architecture, you cannot have an arbitrary long sequence. So this is again the issue that leads to more complex models that are being widely used today, and which is called the problem of long-term sequences. So let's say we have a sequence, it says the clouds are in the sky. Supposing I said the word the clouds are in the, and asked the model to guess what the next word is. The clouds are in the, well, okay, sky is not a very difficult choice. After all, the clouds are in the sky, so we can guess that fairly easily. And so it's easy to predict the last word. When gap between relevant information and place that it's needed in is small, the RNNs can learn to use the past information. So we can input the words from one to the next. So we'd have the being processed here, and then the clouds being processed here, and then we'd have R, and then in the sky, right? So we'd be processing one at a time from the previous time steps to the next one, to the next one, to the next one, so that we can now guess after you have looked at the words are in the last one coming out can be guessed fairly easily. But if you have a very large passage of text, I grew up in France in the beginning, and then the blah, 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 you told a whole story about life story. And then later on, you are asked to guess what is the sentence, I speak fluent dash, what is it? And to be able to predict French, you have to somehow remember that somewhere along the way, you said, I grew up in France, right? So we need the context of France from further back. Right? So the large gap between the relevant information and the point where it is needed. So there's a dot, dot, dot over here that where it is needed here, there are these two highlighted here. So these words are being used somewhere in the past to predict this one over here. Okay, so that's what is being said here. In principle, RNNs can handle it, but fail in practice. And LSTMs offer a solution. So we're going to spend more time on this topic, but a quick look at in the next model. And there is a certain processing unit, you can call it, just like we can think of a processing unit in a neural network, which takes inputs and an activation function and an output. We can think of a different kind of unit called as an LSTM. It's a long short-term memory, and you would input a sequence like best movie ever for sentiment analysis. It would take an embedding, that's the word becomes an embedding or a vector, and that vector goes into this unit called a LSTM. We'll see what that is. And this LSTM unit produces outputs, and this output we just based on best, and then we go to the next word, which is movie here, and this is movie again is processed knowing that the previous word was best, and that produces something using a sigmoid of that. And then when we get the final word here, ever, this ever is influenced by the fact that the previous word was movie and the earlier word was best. So now the output for that, or sigmoid, is a sentiment analysis. This is a problem of sequence to symbol. So is the sentiment positive or negative is what we want to say. Okay, that's positive because the best movie ever is a positive sentiment or a positive review. So we pass in words to an embedding layer and actually train up an embedding with the word to vec. That's what we're doing here. It's good enough to just have embedding layer and let network learn the embedding on its own. So anyway, these embeddings could be learned along the way, or one could use a standard embedding. So those are the options that are being mentioned over here. So a simple sentiment analysis task would be an RNN where a module here is called a LSTM. Well, previously we just showed it as a module A, which is something that is processing matrices. This is a specialized module here, which does something more than the typical unit, which multiplies the weights coming in and adds them up and gets activation. So what is this LSTM? LSTM is a module which requires a little more complicated diagrams. If you think of a standard RNN as like this, from one stage we are going to the next time step and next one. This is xt minus 1 and xt and xt plus 1. We are computing ht minus 1, so these are the outputs. And we are taking into account the input coming in from the previous node. And then what is coming in from here, we can think of this as addition of the two or a concatenation of the two going into a tanh. If you're using tanh as the activation function, and that is what produces the output, and that is what's being passed along to the next time step. So in the next time step, it takes into account what was previously said, and that's what produces the output over here. This is a standard RNN. RNN has nothing special about it here other than multiplying these things in this way. And we are passing it along so that the X's now get converted into H's. And we could do the backprop to learn these weights needed and so on. LSTM is a little more complicated. This module in the middle, instead of having the simple tanh, it's got a little bit more mechanisms going on here. It has got this X coming in, and there's a sigmoid here and a sigmoid here and a sigmoid here. All that a sigmoid does is convert it into a value between 0 and 1. What is the input to this sigmoid? It takes this X as input, and it takes the value coming from the previous stage, what was coming over here earlier on. It is taking that, and that value and these two concatenate together, sigmoid goes here. And there are two things coming from the previous stage. One is the context information, and the other one is this control information here. And that's going to let this thing through. And then there is one more. This tanh is interacting with a sigmoid of this combination input again. And that tanh is producing some other control here once again. And then similarly, there's a sigmoid of this value once again participating. There's another tanh over here. And there is an output and that goes off. So there are two things going in here. One is the context information passing through. And then there is all this control information coming in here. And let's take a look at what is all this here. There are three gates of the form here, what are called as forget gate, input gate, and output gate. And a sigmoid again is a 0 or 1, allows input to go through or not. That is a very simple gate, right? So what is this forget gate? This first thing here is called a forget gate. And what is that function? Forget gate ft is a sigmoid of wf, some set of weights, multiplying ht minus 1 xt. So it's a concatenation of ht minus 1, what's coming in here, and xt. And the sigmoid takes that as input with a certain bias. And that is going up here to interact with the context information coming in. And it is about, for example, if we're changing the context of a word, we're first talking about a male, and then let's say we're talking about a female, then we have to say forget gender of the old subject. The new subject has a different gender, he's become she's, and so on. And what is this input gate? Input gate is the architecture that is shown over here. And what is involved here is there is an IT, which is a sigmoid of W involving, that's similar to what we just saw previously. And there is a C is the context, C tilde of T is equal to tan h. Tan h is nothing but a -1 + 1 type of function, which has got a bias, that's got a set of weights WC and concatenated HT -1 and HT. So we have here these quantities C tilde as well as IT being computed. I guess this diagram, oh, there is a C tilde that's just above the tan H. And what is that C tilde? It is being mentioned over here. And then there is this CT. I guess we're trying to explain this input gate fully. This part of it is being explained in this part, and the upper part of it is being explained over here. That CT is equal to, it involves C tilde hat or CT tilde as well as CT -1, what's coming in over here. And this is actually being multiplied or convolved here, I guess, multiplied, let's say. And that is your value of CT. So what's being passed? So what is happening here is there's some context information coming in, and there is some controls happening based on what is happening on the input. And that causes certain things to be remembered or forgotten. There was a forget that was happening, and then the input is being processed together with the previous context. So that is, so the input is being processed here, xt, and then this, what is being passed to the next stage based on the input as well as the previous context. And then what is this output gate? Output gate is the part, I'm having a hard time with this. Okay, who's on view? Okay, so that's better. So we have whether subject singular or plural and this kind of thing in the output gate is being formed. The OT, this says, what is this OT? Is a sigmoid of this quantity, and HT is what is being input, what is being produced as output here, which depends on this OT here as well as the HT -1 that is coming in here. So it's a bit complicated. So we have, but it's useful to remember what is happening here. Basically, we are passing along information on what has been represented in this input or a hidden layer from one stage to the next. And that hidden layer contains the wealth of information. It is processing what is the current input and what is the context that is coming in here. And so it has to remember this vector with and the weights that cause it to have a value remembers all the past information. And now we are using the current information to process that and update it. That same thing is being done in a more complicated way by using forget gates, input gates, output gates. But as you can see, the equations are all fairly straightforward when you take a look at it. Sigmoids produce a value between 0 and 1. Tan H's produce a value between -1 and +1. That's all that is happening. So these gates are somehow controlled. That's why they call gate. Gate means open the gate, close the gate. Allow it to go through or don't allow it to go through. And then similarly, the output is also being controlled. What is being produced, the CT, what are you going to pass on to the next one, and what is being output over here. So those are two different things. So H is a different from the C, which we saw earlier on. There was some indication of that the context information and the output information could be the same or need not be the same. Here, they're not the same. So LSTM gives a hint as to what might be coming up next in more sophisticated models of processing sequential data. Before moving on, I found this in the Wikipedia on LSTM, a different diagram, so I just thought I'd share it with you here. A common LSTM unit is composed of a cell, an input gate, an output gate, and a forget gate. So they're saying, so there is a cell CT here, it's called the cell here, and then there is an input gate, there is a forget gate, there is an output gate. And what are these here? This is a sigmoid over here, this is a sigmoid over here. So whatever xt has come in, there's a sigmoid function here, and that is being concatenated with this whatever is being set by the input gate, And together that influences the CT value. The CT value in turn is influenced by the forget gate as to what is remembered. And then the output gate, which controls what should be what should be passed along, is influenced by this output gate again. And that's what causes the HT value to go. I think they called it as a peephole LSTM in the Wikipedia article. It's not as clear as some of the earlier discussion we had, but there is another look at it. This slide is an interesting slide. It's a summary of neural sequential models up to this point that we have seen. So once again, let us look at what we have learned so far. Recurrent neural network. RNN is again input, feed forward network, output. The only thing is the hidden layers are being fed back in. That we say that is an RNN. We unroll it to create an unrolled RNN. This is over a time period here, that what is applied at time step 1 creates it output here, and that information gets passed along to the next step, and then which takes as input the next input, and then it takes into account what was previously applied. So when we go to the last word over here, it would have the context of all the previous words. So that would produce the corresponding output. If it is sentiment analysis, this would be the one that's producing what the review is about, positive or negative, or we are producing translations as we are going along, and hopefully the translation, after it stabilizes, it gets a good translation from the last output here based on what all is being seen sequentially. So we can say inputs x equal to x1 through xt, hidden units h equal to h1 through ht, outputs are y equal to y1 through yt, and non-linearity that's being used is h. And the non-linearity is what? H of wxht, whh, ht minus 1 plus bh. We just saw that, what these are. Input x is multiplied by wxh, and the ht minus 1 is being multiplied by whh. There is also a bias term, produce ht. And then yt itself has its own set of weights. So this is again a fairly straightforward set of equations defining standard RNN. So this one here is a bidirectional RNN. So that's an important concept again to be aware of, because some of these today's fancy models use bidirectionality. So bidirectional.
Professor, there is a question.
Yeah, go ahead.
The question is, so LSTM uses multiple operations on the input, context, and the hidden state.
Mm-hmm.
So instead of applying so many operations, we can replace them using two simple weight vectors as an RNN, assuming universal approximation theorem learns the operation of the LSTM gates. Why don't we do it?
Yeah, we'll see that. Actually, we will see what's called as RNN can be used to approximate using the universal approximation theorem. And we refer to it as a universal Turing machine, actually. You can compute anything you want. So that gets into a little bit more of the computational issues. And today what I'm doing is I'm just giving you a sense for what all there is in this topic. We'll once again take a look at all of that. You may want to look ahead a little bit about what you just mentioned about universal approximation theorem, as well as RNN as a universal Turing machine. I think those are related topics that comes up a bit later. These are all, what we're trying to get is get a sense for what is the computation. So LSTMs were the next good thing after RNN. But today, even LSTMs have been abandoned, and we have moved on to other things, what are called as transformer context and so on. I think maybe you're referring to that when you say we can just treat it as a vector. That's exactly what is happening today, all right? So LSTMs were introduced as a method to remember all this context, yet get away from some of the issues of vanishing, exploding gradients, and so on. So that is my take on why were LSTMs introduced and why weren't RNNs good? And then what is their drawback with LSTMs and why were attention models used and so on. So there is a sequence in all of this. Anyway, let's start with the simple things because I think it's necessary to begin like this to know what exactly is happening in these computations so that we can appreciate the next thing better. So let's, okay, RNN we finished. And so I'm going to go through first RNN, then bidirectional RNN, again, deep bidirectional RNN, and then again LSTM. So we'll come back to LSTM again. So let's see. In the bidirectional RNN, the goal is we not only have hidden units in the forward direction H, we also have hidden values in the backward directions H. So there are two directions here. How do you accomplish that? So you are going from X1, X2, X3, X4, forward direction would be this H1, H2, H3, H4. These are all forward. And these values are being sent to the next level here, X1, X2, X3, X4. And we're saying, why don't we have this H4 influence, H3, H3 influence, H2, H2 influence, H1? That's the backward direction. Because we have a sequence that we can observe both ways, as if we have read the forwards and we can now scan it forward to backward, forward, or we can scan it backward to determine what we are trying to translate those four words, let's say. So you see, that's what all these diagrams are. So this is first shown as a this is called a circuit diagram type of notation here, and this is the unrolled version here. And so the output here depends both on the forward direction as well on the backward direction, together determine the output. So this way a translation can have a better appreciation of what all was the input and not only in the forward way when you're trying to make a translation. So again, these are all inputs X's, hidden units H forward and H backward, and the outputs are the same. Non-linearities are similar. H output looks similar. This is in the forward way. In the backward way, they look similar. And the Y's now is a combination of the forwards and the backwards together produce the output. That's a bidirectional RNN. A deep bidirectional RNN would have, of course, many layers like this. So this would have forward, backward in the first stage and forward, backward in the second stage. And then the output, we can say that is a deep bidirectional RNN. Some of these fancy models today, I believe they use like BERT. BERT is a transformer-based model which uses the B stands for bidirectional. So it's useful to know what is this bidirectional. And of course, they would be using deep bidirectional methods. So this one is again putting this in the context of LSTMs. It's again going from X1 through Y1, X2 to Y2, X3 to Y3, X4 to Y4. Just like all of this, except this diagram here has been replaced by this more complicated diagram here, which uses the cell diagram I showed you earlier on, the kind of stuff from Wikipedia. So they're showing what's happening, a forget gate and an input gate and an output gate and so on. So all of these together is, so overall the architecture is quite same thing, except the unit has been replaced by not the simple activations here anymore, by something involving ways of remembering what was happening in the past. So LSTM was a way of using this contextual information in a more practical way than the previous methods. All right. So of course, this is not the end of the story. Like one of you asked this question. So there is this was I'm just going through a in a way historical sequence. RNN came first, came CNN, then came RNN, then came bidirectional RNN, deep bidirectional RNN, and then came LSTM, and then we'll move on. Okay, so we're moving on here is. This is not my full lecture on attention models. I just wanted to introduce it in the overview, and we'll again spend some time when we go into NLP to talk about it. So what are these attention mechanisms? Long-range dependencies are still a problem with LSTMs. Okay. So, I mean, it can be more efficient with respect to gradients and all that, but still remembering long sequences. With attention mechanism, we no longer try to encode the full source sentence into a fixed length vector. Remember, in throughout, we are kind of, that context CT is being passed along. And that has to remember all the information that was in present. With the attention mechanism, we no longer try to encode the full source sentence. Rather, we allow the decoder to attend to different parts of the source sentence at each step of the output generation. So that's where some cleverness comes in terms of which are the parts that one has to remember. I suppose LSTM was trying to do that in some sense about gender and all that, what we have to remember. So this is a more, it's a better generalization. Attention is simply a vector, just like we saw that CT-1. Often the outputs of dense layer using softmax function. So it is just another vector that's being passed from stage to stage. So there is a cleverness being used beyond the idea of simple LSTM units. A quick look here on the attention mechanism in translation. We are again going from an input sequence X1 through XT through to an output sequence, again YT-1, YT, etc. And there is a forward backward things going on here. This looks like it's a backward over here, and this one looks like a forward over here. And the forward and backward information with corresponding weights are being composed here in some suitable way. And that in turn is going along to the next level, which is using the contextual information coming from the previous stage to this stage. So translated, why are translated words, X are source words, use of bidirectional, so this is using bidirectional, it is not, is unimportant, although the practical ones seem to use it. Each decoder output word now depends on a weighted combination of all the input states, not just the last state. It is using all of these input states. And A's are weights for each input state. So in the sense, the previous one was using just a single vector. You can think of it as a last state that was being provided. So this is using some weightage of all of the previous states here. So these are all the previous states that were all observed. All of them are being taken into input. A is a weights for each input state. If A32 is large, decoder pays attention to second state in source sentence while producing third word of target, and A's are normalized to sum to 1. So each of these states are being processed together with different weightages associated with each of them, rather than only one. You can think of the previous model we saw with LSTM and RNN as being only one state being used. Here we are using several states with some weightage with all of it. And the attention means that some states are being given higher importance. So all of the contextual information is of the, so when you are processing language going through, it's all being processed into sequence of numbers, which are vectors, and all the context is being saved in these. In these attention, there is a lot to all of this topic. Again, it's an exploding topic today. We have these words being processed into encoders, which are being processed into these attention vectors here, and then these attention vectors together somehow they are being organized somehow in a hierarchical way. So it's not like we have one vector for each state. These could all be combined together in a hierarchical way. So it could be a smaller vector than all of them together. So it is not necessarily over the whole time sequence, but can be combined. What do I have here? Deep learning and graphical model. Okay, what this set of slides is doing is, I'm trying to give you a sense for all the topics without really covering everything in great detail for now. And graphical models also play a role in all of these. And in deep learning, classification, feature learning. Anyway, this is about how graphical models also come into play in terms of neurosymbolic methods and so on, where we are not just using neural models, but also symbolic models where we can talk about reasoning and so on. So let's not do that too much right now. Oh, okay, hybrid graphical models and neural networks. This does give a little bit of a sense for the last slide that I had. How do you combine these things? Um, Hybrid neural networks and hidden Markov model. So we have a neural network here, and we have some sequence coming in here, which is being processed, and then at time step one, there is a whole sequence here, and the next one there's a whole sequence, and then these are all being related one next to the other. So it is some kind of a hybrid. This looks like a standard probabilistic graphical model. This is actually what is called as a hidden Markov model, which is actually a Bayesian network or a directed graphical model. This is not a neural network. It's a directed graphical model, which is working with outputs of a neural model, and then it is doing some symbolic reasoning with them to produce what the state should be. All right, these are the observables and what should be the states. And what do we have here? Oh, this is an undirected graphical model. This is called what's called as a factor graph here. These squares here says that there is a dependency between these states, but it doesn't say the dependency is directional. It is non-directional. And what is the factors that influence different values? So we can have a directed model or an undirected model to do reasoning between. So it could be a higher level processing where we are going from language into reasoning. And this is a hybrid RNN plus HMM. So we have this is a recurrent neural network we saw with a backward forward. And so that is again being processed with RNN plus HMM. I guess hybrid in the sense forward backward here. Hybrid CNN plus, so there's combination of these things all coming into. So one could incorporate all of these things into some kind of a reasoning mechanism. So there is let me use that to launch off a little bit on an issue here in deep networks today. People are asking the question that are deep networks enough to do everything that the human mind can do? Today, they're very good, but still, can they do everything that human beings can do? Not really. So we haven't achieved, what is called as general intelligence, right? General intelligence has not been achieved. Otherwise, everything would be run by computers today. And then we can ask the question, so what does it take to push all this technology further so that we can have artificial general intelligence, right? Is it going to be just neural networks or deep networks, or is it going to be some combination like this, which is some kind of a symbolic reasoning at a higher level, which is the kind of thing we do when we logically reason out things, right? Old style AI was that. Old style of AI was logic, that we think through and we are able to manipulate symbols and say, if this is true, then this must be true, that kind of a thing. Whereas these neural networks don't work like that at all. They're producing outputs by just these vector multiplications. So the argument here is the issue here is, are you a believer in deep neural networks being able to solve every problem entirely? Or is it going to require symbolic mechanisms operating on top of deep neural networks of the kind we are seeing here? So we can say, well, for now, we probably definitely need the symbolic reasoning methods in today's world, that we haven't achieved it. So if you want to do some higher level reasoning, you need to have that symbolic reasoning as a top layer, and all the basics like the vision, computer vision, and the speech recognition, and machine translation, and all that can be done by the neural models. But anything more may need something. But what about in the longer run is the interesting question. And that question can be answered by first looking at the human brain. We talked about, neural models, how the human brain has about 10 billion neurons. Those are just the units, right? Then we can ask the question, how many synapses are there? Those are the connections and those are the weights. And the number of weights in the human brain with 10 billion neurons is the order of trillions. We have trillions of weights running around in our heads, which allow us to do things. And what about the GPUs and so on of today? Can they handle trillions of weights? Apparently not. So today's network are not capable of dealing with that many weights and doing all backprop with all of them and so on. So one could argue that, well, once you're able to handle that level of neural processing, you're going to be able to do all symbolic reasoning as well. So the argument there is that this kind of deep learning, just dealing with everything as vectors, the attention vector is a vector, everything is a vector, is going to be the solution even to the most complex reasoning problems that might occur down the line. Right? So the answer here is, in the short term, symbolic reasoning. In the long term, maybe the symbolic reasoning is not needed. We're going to be doing it all with more sophisticated attention models. Anyway, that's stay tuned, more to come. Right. So that's all we have for today's lecture. I'm going to do all the nitty-gritties of computational graphs unfolding. We got a second pass on all of the topics of today in subsequent lectures. Okay. All right.